papers, maybe, I don't know, 300 or something like that, are on the type, on the family of mean field game, forward, backward, which I discussed this morning. But there are 4 families at the moment, and now I'm going to speak about second family, which called, let's say, mean field game monotone system. And I think for application, there is a real potential of numerous application of monotone system, and I want to advertise on that and explain why and how to use a monotone system, and try. Sometimes there is a confusion that all mean field game are this forward-backward story, why monotone system are something else, different class of mathematics, different tools, and to deal with something very different. So this morning the idea that there was no global risk, any player has his own personal risk. Why now it's just the contrary. Most of the risk is the same for everyone. So we'll see that. So now there is a finite number of states. So agents could be in state 1, 2, 3, 5, 9, 10, and n, and there is still a continuum of players. So, but they could be in a finite number of states, and you see I called mj number of people in state J. So that's the quantity of player in state G. Previously the state was called X. Now it's an integer and it's called J. And so now the question is, will I stay in state J, or will I move to another state, or will I go out of the game, or will I enter the game? And what will be random in this setting will be this number. There will be randomness about the number of people in state J, and this randomness is a risk, which is a risk for everyone. So here are the something very typical. Or most monotone system will write like that. There will be some differences in example, but that's the typical case. So, so the payoff for a player, I take the stationary case here. Often in example, in application, it's stationary. The payoff is some expectation of utility. So this function b beta g is given. This is given. And the dynamic of the number of people in each state is given by a diffusion process like that. So meaning that for each j, we will have something like, alpha j of u1 un dt plus sigma j, or sigma, let's say dbj. So what is special and important for application is that the change, and we will see why, the change of the number of people in state J depends on the utility to be in other places. this is the utility to be in state G. Utility being defined by this expectation. So in example, well, this is the utility to be here. In this example, I have not detailed why people, why the number of people change, and so we will see an example where these coefficients come out from decision of players. But anyway, in this setting, in this framework, what one has to solve is a set of partial differential equations here, which n PDEs, and all these PDEs have the same coefficient here and here, and are linked together by the coefficient.
So this is the backward part, not the bottom.
So it's, yeah, and there is just a backward part, let's say, because the forward part, which is the dynamic of the population, is included in the backward expectation, which is written here.
So this is not a special case of what you said before?
No, it's not. It's not a special case.
It's a different.
It's a different case. So you forward, backward. So the thing is the following: you have forward, backward system, like this morning. You have monotone system.
So can you write down?
And you have the master equation. So the master equation is something which is very general. If you discretize the master equation, and if there is a lot of noise in the master equation, you will get a monotone system. If there is no noise in the master equation, and you take the characteristic, here are the characteristic. No noise in the master equation, take the characteristic, you will have the forward-backward system.
Why do you call this a monotone system?
So, okay, good question. Let me explain why I call, now it's not monotone yet, it will be monotone when alpha and beta will be monotone function. So let me explain why monotone function. So the best way to have to get an intuition about this system is to look to some specific case, which is the following. Let's consider the following Hamilton-Jacobi equation. So I take a function phi from Rn to R, and I write the following system. Well, Hamilton-Jacobi equation, sorry, plus, and phi is a function of, this is the name of the variables. It's the name of the variable. So it's a function of m, and this is a gradient on m, it's a Laplacian on m. Okay. So this is an Hamilton-Jacobi equation. So for example, let's consider a special case, the quadratic case. So if I look to this usual Hamilton-Jacobi equation, standard one, and now, maybe put also some function f of m. let's call it f of n, capital. I can define the derivative. So the derivative with respect to mg, I call it ug. And I compute the equation satisfied by u. So I derive this and find this, to derive this with respect to mg. So 0 equal minus RUG. So this is the sum. I have to derive the sum of on all k of plus, so I have to take this derivative, plus epsilon, so I commute the derivative assuming smoothness of everything. I will have the derivative of ug plus fg of n, where fg is the derivative of f with respect to mg. So just deriving that, I have to compute that. So maybe the best is I go here. So this is the sum of dphi over dmk of second derivative mgmk so this is the sum of, this is uk and this is dui over dmk. So assuming smoothness, assuming that I permute derivation. So you see that this appear, which means that we have something which starts like a fluid dynamic, which is uk duj over dmk plus epsilon plus fg. So you see, this is a typical example. If the function f, for example, is concave, this will be the gradient of a concave function. And what do we know about the gradient of a concave function? So small f equals the gradient of capital F. If f concave, so means minus f is convex, mean that minus f is the gradient of a concave function, so minus f is monotone. Monotone meaning that minus f of x minus f of a minus, so plus f of b, scalar a minus b is positive for all a and b. So it's monotonicity in the sense of the gradient of convex function, or in monotonicity of an operator from Rn to Rn. So that's why we take the name monotone system. It's because what is interesting is when alpha and beta, change sign, are monotone functions. Depends if you minimize or maximize, etc. So for example, here, the function alpha, which is here, it's alpha k of u is just uk. Meaning that alpha is just the identity. And so alpha from Rn to Rn is just u, which is a monotone function, of course. So that's why the name monotone system.
So here, can you explain what's exactly the equation down there? So you specify m. You specify u of m.
You specify alpha and beta. And alpha and beta are given function, and you compute u, solution of that.
Then why do you have the relation uj equals expectation up there?
Because if you have that and that, if this is a if this is
okay, this is a Kolmogorov equation. That's
yeah.
There is no optimization.
There is no optimization.
No, I put here alpha comes from something else, which I will explain on example. Alpha comes from agent's behavior, but I have not described agent's behavior. I will describe it on example. It's more. It will be more clear. Let's say. You see. So here I have put in things. We don't know why there is such a dynamic, but in fact the dynamics come from a mechanism which is the way the agents play, which is somewhere else. Okay? Maybe I give you an example and
Alpha only depends on u, not
yeah,
directly
sure.
on n.
So let me give you a first example. So I will give you an example which is something, a stylized industry. So, well, I go to the first example and you will see. So I will come back to that later. So,
excuse me, before you go to the examples in this equation, so what plays the role of the space variable is actually the number of agents in states J, right?
yeah.
It's a kind of density variable. You have an equation posed on the space of density variables.
Exactly. Exactly. That's why I keep the name M. Well, there is a great temptation to call it X because, well, okay, so let's keep M. M is the number of the quantity. So let me show you a first example, which is a kind of stylized dynamic of capacity in an industry. So suppose that, in fact, we have only one state, and M1 at time t is the quantity. You can think of any industry, quantity of power plant, for example. Let's think to electricity, because I will go on an electricity model. The quantity of power plant at time t that's the capacity to produce of some industry, let's say electricity. So, okay, so now some of these will go out, and maybe some people will build new unit. So there is a price to build new unit. Let's say that producing a flow Q of new unit cost C of Q. Maybe I will take the example which is more easy for computation, Q square over 2. So there is an industry to build new capacity, to build new PowerPoint, and if you want to build more PowerPoint at the same time, the industry which build PowerPoint will price you more. So if you want to enter this business, if you want to be part of the power plant, if you want to buy a unit, you have to go and buy a unit, and it's a competitive market in amount. So the players, the entrance is a competitive market. The guys who want to enter have to go to the market, to the producer of power plant, and they have to compete to that, and there will be a marginal price, C prime of Q, to build a new unit. Here, in the example, the marginal price will be Q, will depend on how much people want to build something at time t. Now, if you enter that, you will be a power plant. As a power plant, you will own money because you will produce electricity. Then there is a utility at time t. It's the expected value of profit per unit of capacity. Of capacity of one power plant. If you buy 1 unit of power plant, that's what you are. So, in a competitive market, the marginal cost of a unit to enter should be equal to the value you get if you enter. So, the optimal flow at time t should be equal to the utility to have a power plant. Okay, so here in this case means that the optimal flow will satisfy that. That will be the flow of entrance in the industry of power plant. Now, in this example, I have the beginning of the dynamic of M. dm1 dt equal u1 of t dt, and now maybe other things, but that's the flow of entrance. So maybe there is something else. Maybe there is something that the fact that from time to time units broke and disappear, or for some reason there are old plants and so on, and you may have something like disappearing at a rate delta. So some of the plants are destroyed because they are old and randomly they disappear. And maybe you may have some random noise because, well, in fact, they don't disappear in a deterministic way, but in a random way, and maybe it would be better to say that they disappear on a Poisson process, but it's more simple for the mathematics to put this term, it's, let's say, this is to take account of old power plants. So it's a very stylized story, so I make it like that. So here you see how comes the alpha of u, which is in fact all this here. It's an alpha of u and m here. But the main interesting point is that it's a monotone function of u. And here we are in dimension 1. So it's a very simple story because we have only one state, and the game is only, do I enter or not this industry? So the only decision is, will I enter or will not enter this? And the decision is only, what is the price to enter? If the price to enter is lower than the utility I will enter, if it's greater, I will not enter. So the equilibrium price is satisfied if this equation is satisfied. So from game theory, it's economics. Well, from game theory, it's not very strategic. There is just one decision. You enter, and when you are in, you are in, and you, at some point, you will disappear because too old. But you are here, and you are stuck in. So it's a very simple story. Nevertheless, if you write that, then you will have to write to compute u. You will have to write the equation satisfied by u, and so now you have to say, well, how I'm going to make money. So if I'm a power plant, I will produce. There may be a demand for electricity. So there will be some demand function depending on the price of electricity. And the demand should be equal to the offer. The offer is equal to M1 at time t. So M1 is the number of power plant. The demand, you have a demand function, which is exogenous. And this gives you the price at time t. So from M1, you can deduce what the price at time t, and how much money I will make with my unit of power plant. Now there is something which is the fact that people prefer to call this x1 of t, because it's the state variable, and usually in models, state variable is called x1. So now I will call it x1, but you must remember that x1 is a number of, just a question of notation. It's a number of people in state 1. Okay, so sorry for this change of notation. Remember that x is just m, so it's exactly the same. So now, if you want to compute the equation of u, in an intuitive way, the intuitive way is just to make the expansion. So u at time x is the expected value of u at time t plus dt. So at time t plus dt, given that there is a discount rate, and given that you can disappear, that's the delta. It's a and delta. You can disappear, and the utility will change because the number of the quantity of people will change. X is m. And this is what that's the money you make during time dt, is the price minus your cost to produce. So take an expansion of that. If there is no noise, you get just this equation. And the function here is just comes just from G is Q is U. Sorry, is in fact U minus the people who disappear, and also the fact that if U is less than 0, no one enter. So so this equation here writes 0 equal minus R plus, with this notation, R plus delta U plus U minus delta U prime plus some function, if I kept U of M plus a function F of M. So you see now how the alpha of U comes out from the computation. It comes out from the decision of entrant people. The greater U, the more entrant, and this is the risk of the people which are in. If you have a power plant, what is the risk? The risk is that other power plants are built. If there are more power plants, the price will decrease, and you will make less money because there are more power plants. The price of electricity will decrease, and so the expected value of U will decrease. Here is the loop. So you see, what makes the story very different from forward-backward is that everyone here face the same risk, and the risk is a risk of new people entering, well, good news is when someone go out. When some plants go out, it's a good news because there are less power plants, so price will go up. If there are new entrants, bad news, because more power plants and price go down. But all the population of power plant face the same risk. So it's a very simple example here because I have only one type of power plant, and so it's interesting to see what happens if there are two types of power plants. So a good example is to look to the case with two types of power plant, and then you can look to n power plant, a very general case. So what is a little bit realistic, let's say, or it's stylized story. In power plant you have either nuclear energy, which is expensive to build, but then produce inexpensive energy, or you have gas plants, which are inexpensive to build, but then produce expensive energy. So in the electricity world, you have these two types of power plant. One expensive to build, inexpensive to produce, and the reverse. But also there is two markets in energy. There are peak hours and off-peak hours. During peak hours, there is a high demand for energy, and the reverse off-peak hours. So, what does this mean? It means that during peak hours, the demand, as a function of price, the demand is very high, and so this is the offer curve. So when the demand is high, both nuclear plants and gas plants will produce, and the equilibrium will be here. And during off-peak hours, the demand is low, so you shut down the gas plant because they produce too expensive electricity. So during off-peak hours, the gas plants are out, and you have only the nuclear plants which produce, and the price is low. So half of the day you have a high price, and every plant is working, and half of the day you have only the nuclear plants which produce, and you have low price. So you see, with two types of power plants and two types of industries, the day break in two parts. So you can think it's half-half or 1/3, 2/3, or well, it's something given. But the fact that there is two markets means that if you compute the utility, that's the utility of power plant of type 1, that's the utility of power plant of type 2, depends on the number of plants of type 1 and type 2. And because everything depends on the number of plants of type 1 and 2, because some will work during off-peak hours, some will work all the time. So if you take an example, and well, if you choose to have a cost function to produce new units, so for example, it costs more to produce unit of power plant of type 1 than power plant of type 2. So it costs more to produce a new unit of type 1. But then the reverse, this is the price. It costs a lot to produce a unit of type 1, but that's the price to produce a unit of electricity for type 1. So type 1 is very expensive to build, but produce cheap electricity. Type 2 is inexpensive to build, but produce high price electricity. So this will be the price of electricity in off-peak hours. This will be the price of electricity in peak hours. And so the winning will be different for type 1 and type 2. So that will be the profit of type I during one day, which will depend if I equal 1 or 2, because type 1 works all the day and type 2 works half of the day. So the equation satisfied by U1, there will be a difference in the profit, while the first part of the equation will be the same, because the first part depends only on the change in x1 and x2. This means that when you make all the expansion and compute the equation, you find two equations for U1 and U2 with coefficients here which are the same in front of the derivative of U1 and U2, and two different functions here. And you see that the functions which appear here are due to the move of x1 and x2, the move of x1 and x2, which are only function of U1 and U2, meaning that you enter the industry of type 1 or you enter the industry of type 2 at speed g1 and at speed g2. And so that's how we came out with a system which is of type minus blah plus alpha blah blah plus f, as I said at the beginning. So you see the game, the game and the decision of the player build this function g1 and g2. And that's why at first time we don't see where G1 and G2 come. G1 and G2 come from the game to enter state 1 or state 2. Maybe I've been a little too fast on that. Okay. So what happened in
why is it still MFG?
It's mean field game.
MFG?
It's mean field game because there is a continuum of player, there is a flow of entrant. Each entrant only takes everything as given and compute the optimal choice for him given what's going on. He takes as given the function u. He takes as given the function u, he knows the solution of that, he knows u, and he decides to enter knowing u. And u gives him all the signal he needs to decide if he enter or not. And that's why it's it's a mean field game with entrant and people going in and out. So you can say, well, there is a state of the world more, which is the outside. So you go from outside to the industry if you want to have a closed world. But you can say it's a mean field game with entrant and people going out. And of course, if you have a master equation and you discretize it, so it's a very rough discretization because here we have only two states, while going from a continuous to two states, it's very tough. If you discretize the master equation, you may say, oh, I want to have 100 state of the world to discretize. To have a more precise discretization of the world. So here is the first example. So one can discuss the discussion, the general discussion when you get such an equation is is this a gradient of an Hamilton-Jacobi equation? So when you get a system like that, once you get an equation like that, the question is uj the derivative of some function phi? So in order to hope to have that, the alpha should be the gradient of some function g, and the beta should be the gradient of some function f, which usually is not the case. Here the answer is yes, because here we have only one coefficient, alpha of u, which is y minus u minus delta. And of course, you can take g of u equal u square over 2 minus delta u. And then the derivative of u is alpha. So in dimension 1, you can always say, okay, I can find something, and if I find that, I can go to the Hamilton-Jacobi equation, which is d of and maybe I will be more pleased to solve this Hamilton-Jacobi equation and then find u as a gradient of phi. So
Where is the master equation here?
so take the master equation and suppose that that u doesn't depend, well, that m of x density is just a constant, doesn't depend on x, because there is just one x. X can take only one value. So the state space is reduced to one value, which is very tough. I mean, so it's a very, very special case.
If it's only one value, there's no decision variable.
Well, the decision variable is just to enter or not.
Two values.
Yeah, so one value is hidden, let's say. The value to be in the outside world is given, it's 0. So there are two values, in fact, but one is hidden by the fact that it's 0. But one state is a very special case. It's an interesting case, but very special. And two state is more elaborate, and n state, of course, is much more elaborate. But of course, in dimension 1, you can always find that, and you can say, oh, this function, I'm going, well, this story, you can take a, you say, okay, 0 equals r plus delta phi plus u prime square minus delta u, sorry, phi u prime square minus delta phi prime plus f of n. So you can say, okay, this, to go from here to here, I take, well, I derive to go here, and u is phi prime. So, are you more happy with this equation or this one? Depends. Well, usually you are more happy with this one, because here you can say, oh, what I want is the viscosity solution. The viscosity solution tells you that even if you, well, there are many solutions if you don't say I want the viscosity solution. So viscosity solution, choose one solution of this equation. Here, it's the same. You want to have, there are many solutions of that with discontinuous u, but you want the one which satisfies what is usually called the entropy condition. Because this equation, you see, you have u prime, that's Berger's story, and u prime give you discontinuity. So you want to choose among the solution. In fact, here, with all this monotone story, you want to choose the increasing u, which has no discontinuity. So maybe I go to another example to give you some flavor. So let's forget for the slide, maybe if it's possible to go up. No? Well, okay, I continue. Is there a possibility to?
Yes.
Well, okay, so I will do it here. It's okay. Let me give you another example which is completely different. It's a story about queuing, and it may introduce well, equilibrium. So it's equilibrium in a queuing context. So suppose that you have a waiting room, let's say, and that you have people arriving. That's a Poisson process. You have a Poisson rate, and here it's nudity, and well, it's servicing. So it's a queuing process, and to simplify it, I will suppose that there is no priority. So you can decide to enter the room, the waiting room, and hopefully someone will come, and someone come at the Poisson process. Someone comes and take you in the waiting room and service you. So it's a post office, but maybe it's a French post office, so there is no line. You enter in the post office, and sometimes the guy come and say, "Oh, you come," and take your letter, and that's it. So, question: why would you enter the room? So, there is a cost of waiting. Cost of waiting, which will be CDT, some constant dt, and there is a reward. So when you are servicing produce a reward. We can say R0. Okay. So when you enter here, of course you look how many people in there. So let's call x of t the number of people in there. So xt equals the number of people at time t in the waiting room. Waiting. So of course, before knowing every detail, if there are too many people in the waiting room, it's not worth waiting a lot for the reward. If there are few people, it's okay. But depends. It depends on the lambda, on the Poisson rate of all Poisson rates. So suppose that lambda is some constant, some given constant. And suppose that mu is something strange, let's say. Maybe not so strange, but there is a it's like that. If there is no people waiting, there is no service. No one. If there are no people in the few people in the waiting room, less than x naught, that no one will service. Okay. If there are people waiting, there will be a service. Okay. Few people, no one appears. A lot of people, some quantity of people, there is some service. So it's a function of x. So, what do we expect? How to model that? So, the utility to be utility, so the expected net gain discounted if you are in the waiting room. So if I want to derive that intuitively, so should be the expected value of what happened at next time. So next time, with probability 1 minus lambda dt, no one come in and no one come out, and also there is a discount, and I will be in state x. Plus, with probability lambda dt, I will be in state x plus, I could say 1, but let's say that epsilon is someone coming in, as we are already a large number of people. That's the size of one person more. When someone come in, it make an epsilon more, but we are already 1,000, so that's why I call this epsilon, and I could say x plus 1 because someone come in, but 1 is a small thing.
So why does the net gain change if somebody comes? Why does the net gain change if somebody enters?
Because this is the expected net gain if you are in the waiting room. If someone more is in the waiting room, it will decrease your probability to go out. Because you go out, well, let's see how you go out. So from time to time, there is a service. So U of x is so from time to time there is a service. So service means that someone come and say, oh, I pick up someone in the waiting room and I serve. So as he pick up someone, your probability to be served is epsilon over x. With probability epsilon over x, you will be served. So you will have the reward. Okay? And with probability 1 minus epsilon over x, you will stay because someone else will be pick up. So you will stay, and well, there will be someone. The number of people will have decreased. So now, if you make a Taylor expansion of that.
Sorry, why do you have this in the very top line, u of x equals 1 minus lambda dt minus mu dt minus, why do you have this extra term?
Here
Top line.
means that you have not been chosen.
Top line, u of x equals 1 minus lambda dt minus mu dt minus, what's the third one?
Discount.
So u of x is equal to the expected value for you at time t plus dt. Whatever situation you will, whatever will happen.
I'm on the very top line of your expression. I just don't understand why there's a third. You've got one. Take off one thing could happen, or the other thing could happen, or
Discount
what's
rate.
This
yeah, what is that?
Discount.
well,
Okay.
no
Okay.
no one enter.
Yeah.
So the Poisson process, no one enter, no one go out, and I have a discounted value of time. So so I discount the next value. So now that you have all this together, you see that this will put you in something like and also I forget something. There is also here, let's say, you have to pay the cost of waiting. And here you have to pay the cost, so it's a minus, the cost of waiting, but it makes something dt square, which we can forget here. So all that together make you something like AU plus B UU prime. If you go to the second derivative, there is a small thing. If you make this n plus n minus the c of the cost, and in fact plus, well, it's not the c of the cost because you have to add up this r0. Okay. So what do you think will be the, well, I leave you play with the solution, which anyway is in the slide, but what do you find as a u, as a function of x? So when you plot u, of course, here people are happy because there is service, not too much waiting because x is not too big. But if x becomes big, there is a point where too many people, too waiting time. So the cost of waiting is greater than the reward, and so that u is negative. So this means that if we are here, and if someone, when someone arrives by the Poisson process, and if we are here, he decides to enter because u is positive. So what I forget, I'm sorry, I should have put here lambda tilde, where lambda tilde is lambda times 1 u positive, because when people arrive, they have to decide whether they enter or not. And if the cost not doing anything is 0, the decision of the player might be to say, oh, I don't enter this room, too much people waiting, I don't enter the game. So the real thing is that here we should not put lambda of dt, which is the Poisson arrival. We should multiply by the decision of the player.
But what is actually occurring here? What is actually a queuing component here? Because really they just pulled out some probability out of the room. So they don't have queue there. What is actually the queuing component here?
Yeah, the queuing here, well, there is no priority in queuing, it's just waiting.
So basically it's a general utility, yeah? So it's general...
So if there are few people in the room, well, of course, you can make a model saying, oh, I want to keep the order of people. Okay, so it's just the same model, but a little bit more complicated because you have to have two variables. Okay, so I made the model a little bit simpler. by saying, okay, there is no priority. You enter the queue, but you go out of the queue randomly. Okay, so it's not queuing, it's waiting.
Yeah.
Okay.
And another question, so they evaluate utility at the current moment of time, so they don't know what will be in the next moment of time.
What is
So here it's purely forward thing, so they just, here it's just current time, yeah?
Yeah.
So if we turn it to the recursion, everything which they know, it's the current time t, yeah?
Current time is t, but it's a stationary story. I don't care about the time, I care about the number of people which are already here.
But if for more than, if for instance we see the situation where at the next stage there will be a lot of people coming in, yeah.
Yes, so my risk is that other people will come.
Yeah.
Okay, that's what happened here. If I enter here, the utility should be positive. The utility is positive because I have good chances to go out, but the number of people is going to increase. And I take the expected value of going out at some time in the future. If I am not chosen here, the number of people will increase, and at some point I will have regrets to be in. But if I am unlucky, there will be more and more people, and the chance to go out will be less and less. But it's only if I am very unlucky. If I enter now here, the computation of the utility function tells me that my chances to go out are very good, and I have chances to get the reward very soon, and it's worth going in. That's the computation of U which told me that. And the interesting part is the following, and here we can see the story. The interesting part is that when you compute U, you find this part. If you enter here, means that there is very little person in the room, in the waiting room. So as there is very little person in the waiting room, there is no service. So why are you entering the room as there is no service? It's because you just anticipate from the fact that other people will enter. So if you enter here, it's because other people will enter. And then at some point we will reach this level, and when we will reach this level, service will begin. So it's because it's an equilibrium. It's because you know that the equilibrium is that you decide to enter. You decide to enter even if there is no service. But you know that randomly other people will arrive. Randomly, when they will arrive, they will have to decide, and they are as smart as you are. They will go in. And all these people going in, we will reach this level, and when we will reach this level, there will be servicing. So that's why people here are not myopic. They are supposed to be smart, know what is the equilibrium. Of course, there is some randomness because arrival are a Poisson process. So there is a small probability that no one comes. So we are few people are here, no one comes in, and we never reach that. So there will be no service, and we will wait and pay the cost and blah blah. Okay. So that's why it is equilibrium. And that's why it's mean field equilibrium, because you take account all potential arrivals, stochastic arrivals, which could be or could not be. Yes.
But basically, I don't know, from the game perspective, I can't see the reason why, if there is an insufficient number of people in the room to start servicing, and all the players know that they would enter. because for them it would be optimal to wait till the time there will be other agents. So of course they may be anticipating that, they're just maximizing their own utility. So
Yeah,
basically,
if a behavior, well, this is a Nash equilibrium, let's say. If you believe in this Nash equilibrium, if you believe that everyone believes in this Nash equilibrium, if this Nash equilibrium is a common knowledge, you enter because you know that other will enter. It's a loop. You think, oh, I'm going to enter because I know that other would enter, and I would be stupid not to enter if other enter.
yeah. So, but once you know that they enter, but it's not worthwhile for you to be the first to enter. That's a problem. So
No, because you have no choice. You arrive by a Poisson process. When you arrive by a Poisson process, you have to take a decision. You just come out from your house, you go to the post office, you look to how many people are waiting there. Oh, not very much, but 15 people are waiting. So 15 people is enough. I will enter the room, we will be 16, and hopefully 3 minutes later we will be 20, and then the post office will start running.
Yes, but then you. Well, the thing is, you have then insensitive to deviate from your strategy. So, for instance, you don't have cost of waiting. So, if you pass by post office and you see 10 people inside, it's your optimal strategy is to pass by on another round when it will be.
Yeah, sure. No, the rule of the game is that you have one chance.
Okay.
If you go out, that's finished. Okay, so it's but it's a special game. You have one chance. Okay. So,
So in fact, there is no time really.
no, in this very simplified story, there is no time. It's just a stationary story, and the new player, when they arrive, either they go in the waiting room or they go out, but they will go out forever. They will not have a second chance. And there is, and it's a stationary process, and it will be a new guy who will come. And, okay. So, thanks. So it's a very special case, but if we, keeping this idea, we made a modeling model for the order book. So a more serious story. So in the order book case, let's join words with Le Halles, Lyons, in La Chapelle. In the order book case, so it's a stylized order book. You have, so it's a special market. So we can say, oh, there is no market like that, but okay, it's stylized market. We say, okay, there are sellers waiting and there are buyers waiting, and the price of buyer and sellers is given by a rule of the market. The price of buyer is a function given by the market of the number of buyers and the number of sellers. So there is a rule in the market which tells you that the price function which gives a price. And the rule of the market is that when there are a lot of buyers, the price should go down, and when there are a lot of sellers, the price should go up. No, the reverse. Okay. So you have two functions, f and g, which are the rule of the market. So f and g are given, are market rule. So it's a way to try to to emulate the way a market, the way it goes in a reasonable market. So sorry, it's not on that. So what's so in this thank you very much. In this setting, I mean we have a flow of arriving buyer, a flow of arriving seller, and buyer and sellers have two choices: either to have an immediate transaction. I want the liquidity. I want to sell just now, and then they will have to sell at the bad price, the price of the buyers. Or I agree to go and wait here to that some buyer come and sell to me and buy to me. Sorry. So this is an arrival Poisson arrival of buyer, Poisson arrival of seller, and then we try to build an equilibrium model in this context with this rule of market to make the decision: what should I choose? And of course, there is in this model there is a cost to wait, either if I am a buyer in this queue or a seller in this queue. So, depending on the size of that and that, we decide for one or the other. So, computations are just the same as previously. But of course, it's you have two functions, U1 and U2, and well, you have to make all the calculus and then all the simulation, but it works, and the picture here means the following. So, our two regions, well, it's symmetric, but okay. So, here it's buy or sell immediately. Here it's enter the queue. So here it's Q buyer, Q seller. So if there are little buyer and little seller, when I come in the market, I enter the queue. If there are a lot of buyer, if there are a lot of buyer, and I want to buy, I should not enter. I should buy. And other people here, the seller enter. And here, the reverse. So enter for and sell. So here are what people do. After all computation, you find that, which is of course natural. You don't if you are a buyer and you see that the queue of buyer is very big, you don't want to wait. You buy immediately. Buy immediately. Here, enter the seller. If you are a seller and there are small amount of seller enter the seller queue. So you obtain this result through same type of computation as the preceding case. I mean, you have to write the U1 and U2 function.
What are the U1 and U2?
So U1 is
What do they represent? So this is
U1 is the expected profit. U1 is the expected profit of someone which is here. So someone who is here, someone who is here, he will wait. There is a cost to wait, but he at some time he will sell at he will buy. He is here. He will buy at this price. So if a buyer enter here, he hopes to buy at this price. Why? If he doesn't enter the queue, he is obliged to pay the high price. So the question is, will this price plus the cost of waiting, is the expected value of this price plus the cost of waiting less than that?
But how do you quantify the cost of waiting?
Oh, it's an exogenous. We say, okay, there is a cost of waiting per unit of time.
Yeah, per unit time, but the length of time, it's random.
Oh, yeah, sure. So it's an expected value. So it's an expected value, and expected value is translated in the equation of U. The equation of U contains the fact that it's an expected value because it depends on the parameter of the Poisson arrival.
So which term here is the cost of waiting?
So here, the cost of waiting, or cost of risk or cost of waiting is here.
So this doesn't depend on QA or QB?
It's per unit of time. So the total cost of waiting is the expected value of that, or multiplied by your expected time of waiting.
But if a QB is large, then I have to wait more.
Yeah, sure. This will appear in the equation of U, because when you write the equation, well, to write the equation of U, you make the expansion of that. You write the PDE satisfied by U, and of course U will be low if it's a cost. So the cost, no, it's minus the cost. So if the Q is very big, the expected time is big, and U is small. And so, in this case, you see that U is smaller than the price that you will get.
So can we think about this as a repeated game? So the player chooses a function U as a strategy, and then you repeat this, and this is a self-consistency equation.
Yeah, it's a self-consistency equation. But it's not the same player which plays a game. It's when you are one player in the crowd, you come to the market, see the state of the market, and you decide. You have to take an immediate decision. You arrive to the market. You look to the size of the queue. For example, if this one is very big, then you will decide to go. If this one is small, you will decide to wait.
Yeah,
and
I understand the idea, but the equation, the U doesn't depend on time, but the right-hand side depends on time.
No, because it's to simplify, I put it stationary. There is a stationary arrival of people. What is not stationary is that maybe people will take some decision today, but then the size of the queue will change, and in the future, because the size of the order book has changed, the decision will be different. But the decision depends only on the size. For the new entrants, the decision depends only on the size of the order books. the bid and ask or the books. So they just look to the market and they decide. I decide because I know that other one will decide in the future. So I anticipate decision of other one in the future. But arrival of other one is random. So there is a risk.
So before there was U positive, which the
Oui.
threshold U positive telling you enter or not. What is it here to decide? I go to the buy, I go to the sell, or I just go home? What is
No, you have to. Here you can't go home. Here the rule of the game is either you take the liquidity from the market or you bring liquidity to the market. Either you decide.
Market order or limit.
Yeah,
and how the decision is made?
it's made by computing your the value U of.
What do you do with U? Before it was U positive.
Here you compare U. Either I go to the seller. Either I enter this waiting place, or I go here. So if I am a seller, this price is low. Either I decide to sell at a low price.
But, you compute U. Imagine that I've solved this beautiful equation. I have U. So now what is the
But is U of that? If you
U is a function of the two
yeah,
height. U is function of QA and QB.
so the question is U. I am a seller. US of QI of QB. Sorry, QS. Is this greater than PB?
Okay, U is in a monetary unit. You can compare.
Yeah, sure. So for example, if I enter that and there are many people arriving and so all the sellers sell immediately, then this will be equal to that. So the expected this U is more or less equal to that if there is no waiting. If the seller Q is small, if QS is very small, so US of small thing epsilon and QB and a small thing is equal to PS. There are very little people in the queue here. I enter the queue, I will go out very soon. So I will sell at this price, which is better than this price. So my decision will, if I see a very small queue, I enter the queue because, the expected value is that I will have that very soon, without the cost of waiting. That's a boundary condition.
But here you assume that the execution rate is exogenous.
The execution price is given by the market.
Execution rate, like the speed of execution is.
Oh no, the speed of execution is given by the fact that there are other people arriving here.
Yeah, so then it's not clear that when QB
Yeah.
is small.
Yeah, it's not clear. You have to think a little bit, okay? When this is small, and a buyer arrives, and this is quite big, he will not go here, because if he go here, not only this is big, but no seller will come, because all sellers will go here. So the buyer who come doesn't go here because he knows that no seller are going here. All sellers are going here. So all buyer has to go here. If this is small, there is, let's say, like an equilibrium, which is buyer must go here and seller must go here. And the liquidity is on the sell side. And that's why we get these two things here, which when you look to the time that people spend, so we compute you can make the dynamics of the market. You can simulate the market, and you can look to the stationary measure. So the time, which is when you look to the market, where is the probability that you see the market? So that's the frequency. The market is often here or here, meaning that it's almost like having two equilibrium. Either the market is here with a small q, qs, and a big qb. Sellers go here because this is small, and buyers go here because they have no hope that a seller will go here. And so sellers and buyers go here, and sellers are very happy because they go to a small q, and someone come to buy them very soon.
So you will have a typical bid-ask imbalance,
Yeah,
which is non-zero and which depends on the cost of waiting.
yeah. So if there is some cost of waiting, well, depends on the parameter, but if there is a cost of waiting enough, there is an imbalance, and the market is higher on the buyer side or on the sell side, and from time to time move to one to the other, but the switch, there is only a switch if the Poisson process by randomness brings you from here to here. But this type of market with switch depends on the cost function, as you say. Okay. Then there are many features because you can have two different populations. You can have high frequency trader, meaning people with big Poisson process and small cost, and mixed with people with high cost and low Poisson and so on. And you can study how this change the equilibrium of the market. Okay, I'm sorry I've been long. Thank you very much.
Any questions before we break?
So I'm afraid that Monotone system, the first time you see them, is not an obvious story. So paper has been written, which may be more clear than what I've been. But I encourage people to look to this type of equilibrium model, as there are challenging mathematical questions and also a lot of application, I think.
So we have a 30-minute break.